Okay, now that we're done with that example problem, we'll go to the calendar and see what we have coming up. We've got the 2 individual design projects due today. There are 2 other sets due 1 week from today, and I'm not trying to kill you guys with homework. You notice that the work you've had to do so far, the first one was actually really straightforward, and it was the second one that was a little more work. That's the same way here with roller bearings and tolerances. The roller bearing problems aren't all that difficult, and the tolerances are even simpler. So I'll leave those due 11:59 a week from today. And so we need to cover tolerances next, which we'll do, and go into some other materials as well. But I'm trying to get all the material in as quickly as possible so that we can work on the project. I think the projects are more interesting. Let's see, let's turn on the next learning module, which is tolerances and fits. So now if we go into it, oh great, let's find that and recreate the link. I'll do that in a minute. With the presentation first. You guys have seen a little bit about tolerances and fits in MET 102. And I should warn you, there is a somewhat of a tradition that was started in this class by Professor Hughes. It was demotivational posters at the first of all the slides, and I've maintained that because I thought it was funny. Apathy, no mountain seems too tall when you don't care about climbing it. I like that. So, not trying to discourage you, I just think it's funny, so start on the last note. All right, tolerancing. In modern manufacturing, we want all parts to be similar enough where they can be interchanged, right? The big revolution in assembly and manufacturing was when they realized, you know what, it's probably best to take the time to make all parts interchangeable. And so in order for parts to be interchangeable, they're not going to be perfect, so they just have to be tolerant. They have to be in close enough size so that they can fit. Now there's a lot to be said about this because the American view has usually been that as long as parts are within so-called tolerance, then they're good parts. The Japanese view has always been, since World War II basically, has been that the farther away the part is from the nominal or the design value, the less the part is worth and the more cost there is to the customer. So you'll learn about that if you take quality control. If we offer it still. I think we do. I've taught it several times. But I stopped teaching it a few years ago when Webster got here. It's one of the classes he took over. And I think he's made some interesting changes in it. If you get the chance to take it, the way I taught it, it was a pretty boring class, but it's probably one of the more valuable classes. Some of the more, you go with your program like this and you think, oh, I'm going to get to design the best gear ever. Well, you don't have to. That's already been done. But controlling quality is something that actually has to be done on an ongoing basis with every new product. So, has anyone had the quality control course here? No? Okay. A lot of people laugh about quality control, but there's some good things to be said there. There's some important things. I see smirks. I have to ask why.
I'm in quality control, so like what you're saying is like, even when a part's within tolerance, our quality manager is like, that's a little too close to the end of the tolerance, like, but it's still in tolerance.
Right, right. So it can be frustrating, right?
Yeah, it is.
But one of the big ideas behind modern quality control is that you continuously improve. It's accepting that we're not going to get it right the first time, we'll do better next time. And it's not a lazy thing, it's just, let's concentrate our efforts, since we only have so much time, let's concentrate our efforts where we'll get the most fruit, and continue to do that. And that's actually a philosophy we use here in teaching. You know, I'd like to teach you the absolute best machine elements course ever, but it's probably not going to happen the first time I teach the course. So I'll do better next time. So you'll notice when I bring up my view of my Blackboard course, I've got a list of things that I want to add or remove or improve in the course. So the idea is continuous improvement. Anyway, back to tolerancing. Ideally, all parts are basically identical. But in reality, there's going to be variation. So we have to have some way of controlling that variation. Now, the problem is that the more precisely you control variation, the more expensive typically it becomes. That's somewhat of a misnomer because that looks just at expense in the manufacturing process. What about when you lose customers because the stuff you're making is crap? That's a big cost too, right? So there's something to be said for making higher quality merchandise. Anyway, so we have to specify dimensions, and we have to decide as engineers what is the appropriate accuracy or precision or tolerance required. Okay, so the idea is that from a manufacturing standpoint, higher accuracy and smaller tolerances lead to expensive parts require a lot of time, and a lot of them have to be thrown away because some are going to be out of tolerance. So a lot of times when you make something, it cannot be remanufactured. You can't take that material and make it right. If it's wrong and it's messed up, it has to be thrown away, and you've got to start again. Low accuracy tolerancing allows large tolerances, sometimes none. It's less expensive, at least up front for manufacturing, but can cause problems down the road. Now, that's a really light overview of tolerance, and there's not a whole lot there. You probably could have told me the same thing before we started. What else can I tell you about tolerancing? Well, there's a couple things. Tolerancing, when you're going to make a lot of something, you're going to make 1 million parts, knowing the appropriate tolerance is, or doing some experiments to determine the appropriate tolerance can be worthwhile. If you're going to make 1 or 2, why not just put enough effort into it that in your judgment you think will be adequate? When I worked for a small company where we built 1 or 2 of each product every year, we had thousands of different products, but we'd only build 1 or 2 of each one every year. There was no point in making a drawing and taking the drawing down to the machine shop, having them build a prototype piece, putting it together to see if it would work, and then have them build another prototype piece, purposely a different size, so I could see if a different tolerance would work. There was no point. I just put a tolerance on my drawings that was based on my own experience, and it was primarily, we're talking about pieces that were sheet metal parts or machine parts primarily, and from my own experience working there, and from asking the other people when I got there, because when you get to your first job, you don't have experience. How do you know what to use? Well, you just ask the guy sitting next to you who's been doing this for the last 20 years, right? Or sometimes the company will have standards. If it's this kind of part, these are the tolerances we use on these parts. If it's a high, and some will even have tiered levels, so a high tolerant or a high precision injection molded part versus a lower precision. When I was at Grody, the lenses that they made had to put light in the right place. I don't know if you know this, but our government does regulate how lights shine out. So for example, your forward headlamps. You guys notice that newer cars have a very sharp cutoff. You shine your lights against a garage door and it's light below and dark above. That was something that, we realized we could do it, and the government said, yes, do it, and so now everybody does that. And the idea is to not shine lights into oncoming drivers' faces. That's the idea. But anyway, so the government does have regulations on all different types of lighting, including marker lamps that Grody was, I don't want to say famous for, but it was their main product line. And the interesting thing about these marker lamps is they consisted of a body that the circuit board and the pins would mount to, and then a lens that went over the top. Well, the body could have a lot more sloppy tolerancing in terms of manufacturing because it was just mounted to the side of something, screwed into place. That could be a lot sloppier than the lens. The lens, especially the optics in the lens, had to be much more precise because the lenses actually had cube features in it so that light coming in would bounce off one angled surface, bounce off the other angled surface, and come back out. That way, if the truck's off to the side of the road and has no power for whatever reason, because of some failure, an oncoming car's headlamps would actually shine light into the reflector and back to the driver so the driver could see the truck, even though the light was not on. So there's a difference in the level of tolerancing and the precision required depending on what the part was, even though both were injection molded parts. Okay? So a lot of times the appropriate level of tolerancing comes from past experience, where we built a lamp and it didn't work, we had to make a tighter tolerance, or hey, we tried loosening up the tolerance on this part, it works fine, had no trouble, so we go with that lower tolerance now. Anyway, this is a good segment into surface finishes because the roughness of those plastic reflectors also had to be controlled. You have a fairly rough surface, the light will not bounce properly. You need fairly polished surfaces. So that was another tolerancing, if you will, that was required. So surface finishes basically indicate the surface roughness, and it's important that parts mate with each other. If you think about that, what we're saying is, if the surface is too rough, the surfaces are going to be held apart, away from each other. Anybody ever rebuild an engine? How many of you rebuilt an engine? Nobody has? I think this is a first. Every time I ask that question in past classes, I've had at least one person raise their hand. I've rebuilt about 5 or 6 now. I'm losing track. I rebuilt my first diesel several years ago. It's the car I drive now. My dad was talking to me about it the other day, and he said, yeah, with all this traveling you're doing, I'm not real comfortable with you driving your car so far. And I said, no problem. I know the mechanic that rebuilt the engine. And we both laughed. Rebuilt. Doesn't mean it's going to last. I might break down and then be embarrassed about it, right? If I didn't do something correctly. But it's been working fine for a while. But when you rebuild an engine, typically you'll end up taking crankshaft out or camshafts out, and you'll have journal bearings. You guys know what journal bearings look like? No? Let me show you. It's worth going into. Yeah, any of these will do. This is fine. This is what a crankshaft looks like. Anyone know how many pistons will ride on this crankshaft? Can you count them? Look down the main line. That's what's going to be mounted in the block. Okay. So these are main journals, just like the note here says. There's 1, 2, 3, 4, 5. The rod journals. This is where the connecting rod will connect up to the piston. And there are 1, 2, 3, 4. So this is a 4-cylinder crankshaft. Now it looks a little bit strange because most 4-cylinder crankshafts look more like this, where they lie, all the journals lie in one plane, okay, where 2 are up, 2 are down. I've never seen one like the picture I happened to find a moment ago, like this one. You notice that, let's see, we've got an angle here. That one looks like it might be almost the same, well, a slightly different angle. They're not, anyway, these rod journals do not all lie in one plane, so I'm not sure what's going on with that engine. That's different than any 4-cylinder I've ever rebuilt. But it does show the surfaces really well. All these surfaces here, you notice how they look, you can just tell they're very polished, right? Okay. In fact, when you pick up a crankshaft or a camshaft, which also has journals on it, and you look at it, those are almost a mirror finish. You can almost see your face in it. You know, it's distorted like a fun house because of the shape of the mirror, but it's still a very fine surface finish. And the reason for that is that the tolerances are very low. The tolerances between, if you think about all these journals, they have to be down almost a perfect line, right? Because the crankshaft is rotating a block. If one's off a little bit, there's going to be wobbling and it won't work. So not only that, but because of the nature of plain journals and the way they work, there's just an oil film between the journal itself and what's called the bearing. Now, if you replace the crankshaft in your car, you ever pull it out, you'll probably put these in. Have you guys seen these before? You know what these are? Okay, well, these are the bearings themselves, and what they are, they actually go around each journal. Okay, and the way it works is there's a very small difference in the diameter, the inside diameter of these bearings and the outside diameter of the journal, and that little bit of clearance is, I don't want to say filled by oil, but oil does go into that clearance, and that's what actually keeps the bearing surface, or the journal surface, from touching the bearing. We'll learn more about journal bearings as we go. There's a whole chapter on plane bearings, and that's what we'll be talking about. But anyway, the reason the surface finish has to be so fine, there's a couple different reasons. But one of the main reasons is the tolerance between the journal and bearing is so small that if the surface was not very smooth, the surfaces would impact each other. There would be wear, very high wear, because of, think about it like sandpaper rubbing. Okay? Sandpaper works at removing material because it has a bunch of ridges and valleys in it, right? Well, that's what we don't want in this crankshaft, is ridges and valleys. So the surface finish on a microscopic level is actually important, or a very fine level. I don't know if I want to say microscopic. Oh, here's what happens when You don't have oil in the bearings like you need, and rubbing actually occurs between the crankshaft and the bearings. These look like rod bearings, and these look like main bearings. That's what I'm guessing they are. It's hard to say. This is a little confusing because usually you have an oil hole. These don't have that, so I'm not sure, unless that's what these grooves are for. I'm not sure. General bearing theory and Lamborghini. I don't know what those are off of. Anyway, so if you look at a surface on a very magnified level, what you will see is many different types of flaws. And there are names for what you see. The general waviness that you see has a name, and it's the true waviness height. Okay, that's how it's quantified. But there's also fine surface roughness. Okay, and so that's waviness really is no, let's see, waviness height. It's been a while since I've looked at this. Waviness width. Here we go. There's waviness width, and there's roughness width and roughness height. So roughness is the fine variation of the surface. Okay. I'm not saying when you look at the surface of metal, it'll look exactly like this. I'm just saying the finer waves are called roughness, and that's the part we're really interested in. There are surface flaws and scratches, for example. You might think of this as looking at an album, a vinyl record. You guys know what a vinyl record is? I was watching, introduced my daughter to Laurel and Hardy. I don't know if you guys ever watched Laurel and Hardy. They were 1920s or so comedians. Some of their movies were silent, some of them were spoken because it was during the time it was transition. And they were going along in their Model T, and they pulled a string and music came on. Well, the music stopped after a while, and they got out, and this is a comedy team, but they opened the hood, and they had a record player under the hood with a string attached to the tone arm, so they could start the music. That was their music box. Of course, the Model Ts weren't actually like that. It was even funny back then. You know, this was something you'd have in your house. It was kind of like throwing a record player in your back seat or something. But anyway, so a record was a vinyl album that had grooves in it, and there was basically a needle that followed those grooves and vibrated and made the sound of the album. Of course, we're way past that nowadays. But this is still relevant to today. Well, almost. I guess you guys are probably getting away from CDs as well, aren't you?
Records are coming back.
Records are coming back.
I've got
That
like
is
10
true.
of them, so.
You got one at home, okay.
I got a bunch of records at home.
Why do you listen to them? I'm just curious.
I just like the sound that it puts out, so.
Okay.
It's
I'm
cool
kinda-
to, I don't know.
It's kind of cool.
It's not old music though, it's like modern, it's like
Right.
modern bands and they all release vinyl. And
Right, yeah.
it's just
If
kind
you
of
ever
cool to
get,
listen to on a record player.
you ever get the chance, look up the channel Applied Science on YouTube. He's a real smart guy. I don't remember his name, but he has a lot of videos. One of the videos he made was the motion of a record needle in a groove. He has a scanning electron microscope, so you can get real nice zoomed in views of things. And he actually cut out a section of vinyl and set it up so that he just put the record needle down into one of the grooves and moved it very finely and took pictures and then put it all together as a video so you could see how a needle would move in the grooves. So it was really interesting because the grooves on either side have ridges in them, what we would call roughness really. And the needle sits down and is deflected in this direction diagonally due to one side and deflected this way, the opposite diagonal, for the other channel. So your channels left and right in stereo on either side of the groove. And then there are detectors on the head so that as the needle deflects this way, it picks it up as the left channel, this way is the right channel. It's pretty clever, it's interesting. And then I was at I like thrift shops because I like not spending a lot of money on stuff. I was at the thrift shop probably a month or two ago, and I found a 4-channel album. I have no idea how it works. I want to figure it out, so I'm going to look into it, see if I can figure it out. But anyway, it's something worth talking about. But yeah, an album is an example of this. And you probably know that sometimes albums get scratched, and when they do, the sound degrades, right? It'll go over that scratch and it'll make it pop every time. Well, that's because the needle is actually detecting this. In fact, one of the ways, there's many ways now. You can use lasers and light to detect this. In fact, you can use lasers to read albums also, which is kind of interesting. But one of the ways to detect surface roughness is by dragging a very fine needle and a very balanced arm that detects motion as the needle rides up and down in all of the waves. And that's one way of measuring surface roughness. All right, typical surface finishes that operations are capable of. Flame cutting is pretty rough. Anyone ever flame cut something? Correct? You end up with a pretty rough side, don't you? Okay, well, that's about 2,000 to 500 microinches is about the surface roughness you can expect from that type of process. There's micrometers up here. It's the same size, but obviously different scale. Forging, 500 to 125 microinches is the approximate roughness. Sawing anywhere from 2,000 all the way down to 63. You can saw things fairly precisely, control it well. Okay. Planing and shaping. You can see as we move down in the table, we're getting to finer and finer tolerances. How about milling, which is something that we are all familiar with? Well, anywhere from 250 down to about 32 microinches. Okay. So if you're running the mill with a really rough pass, taking an awful lot of material, do you expect to be at this end or this end? More rough or less rough? More rough, of course, right? Because as you try to drive the cutter into the material, you're taking a bigger bite and it deflects the cutter farther, right? So you're going to end up with a more rough cut. All right. Let's see, there was one I wanted to bring up and I don't see it here. Discharge machining, there it is. Electro discharge machine, EDM. Anybody ever used EDM for anything? Electro discharge machining is really interesting because basically you put a part, you have the opposite part of what you want to make, typically, and you basically just put the blank material down into a vat of, I think, oil or something, and you apply high voltage across, let's say, the male part, and you drive it. You don't actually drive it into the female part, you get it close to the material, and what happens is sparks jump across and actually blow away material on the workpiece. So you can make the shape that you want. It's really an interesting process. I used it, I was making I was designing a press. It was a cute little thing. It was only about 2 inches square and maybe 3 inches tall. And we had these crimps, and basically they were electrical connectors. They were shaped basically like this. The way it worked is you put them around the wire or through whatever you wanted, and then you need to crimp the legs over, something like that. You've probably seen these if you ever take apart any electronic items that have terminal pins like that on wire, for example. Or if you ever are doing some wiring on your car and you need to crimp another wire or a terminal onto a wire, you can see these. But these were really small. These were only about a 32nd of an inch square. So the press needed was very small. We didn't have one, so I just designed one. Well, the tool needed to cause that crimping action is sort of a, here, let me draw it here. I'll draw it beside so it'll end up on the video. It's a pretty simple shape. You need something about like this. And what happens is it engages with the metal sides, rolls them over as you drive it all together, and it can crimp whatever you want. Okay, it crimps on the wire. Yes, sir?
Is that kind of like the bottom plate on a stapler, sort of?
It is, yeah, it's a whole lot like, excellent example, never thought of that. You're right, it's a lot like that. But since I was dealing with a part that was only a 32nd of an inch, this was a tiny feature, right? And asking the machine shop to make that was not really practical. So what I did is I asked, we had a local company we contracted out to, I had them EDM this, in fact, wire EDM. So the way that works is instead of having an actual shaped part that they would drive into this, instead of having a part that they had to make that looked like this, that they would electro discharge machine it to blow out all this material. Instead, what they did is they used a wire running this way. And a lot like a saw, just ran that wire through the material to make the shape that was needed. And with CNC control, it's easy to make that shape. So they had a very fine wire. And basically, they just ran it through very, very slowly, where the sparks from the wire to the workpiece blew away the material of the workpiece and cut out the part. It was really interesting because in doing this, we had just acquired some equipment from a company called Guide. You probably have never heard of Guide, but Guide worked for GM. They were basically a supplier for GM. They were a huge lighting company. They were in somewhere up in Indiana, I believe, but I don't remember where. So we had just hired a bunch of employees from Guide and bought a lot of their equipment. They were liquidating everything because they were going out of business. And when I did this, one of the former Guide employees said, you know what, we used EDM at Guide, here's what we did. See, headlamps have reflectors on them. Those reflectors need to be highly polished. They need a very fine surface finish. And so one of the ways to make a prototype headlamp is to electro-discharge machine it, make a positive tool, and just drive it into material, slowly, of course, to machine out the shape that's needed. And he said what they did, that the problem is electro-discharge machining did not make quite as fine a surface finish as they would have liked. They needed surface finishes more over in this area, much finer, smoother surfaces. They said they found out how to do it. They took the male tool and they actually vibrated it just a little bit. So as it was machining and driving in, it would actually polish the surface as it went. And they could make very finely. So there are tricks, I guess my point is, there are tricks to getting these different processes to give you a finer surface finish. But you have to know what those tricks are. So anyway, typically a journal on a crankshaft is polished or lapped. That's pretty common. The reason is because you need a fairly fine surface finish on the journals. All right, surface finishing costs, of course, go up. The finer surface you need, the more it costs, and it goes up pretty rapidly. So we're looking at flame cutting, which is fairly inexpensive. Okay, and I think the 100% cost is basically just turning. So on a lathe, the typical finish you get on a lathe, and everything else is compared to that. So these are cheaper processes typically than turning, and these are more expensive processes. You can see how how there's a percent change that increases as you go to finer and finer finishes. All right. Typical numbers. Well, 63 microinches is a typical as machined surface, not a machine surface where you're really hogging through the material, but something where you just normally run the mill and ran with usual feeds and speeds. If you want a 32, which is about twice as fine, it's about a 240% increase in cost. If you want a 16, which is about 4 times better, it costs about 4 times the cost. Now, this surface finish is a common specification in dairy applications. Anybody want to guess why it would be? Why in a dairy application would you want such a fine surface? Yeah.
Those bacteria can't build up in the
Exactly. Bacteria is small. It's on the order of the scratch size. And so you don't want the bacteria building up and ruining the next batch of milk that comes in. Okay. I highly agree. I love milk. When I was a kid, there used to be a dairy farm over here where they've expanded down 62, all the industry that's gone in there. Anyway, there used to be a dairy farm over there, and you can go and get raw milk. I'm not a big raw milk fan, except that it tastes amazing. So it tastes like cream, basically. So anyway.
To go farmers in Southburg we go to.
Yeah, I've been there. I'm just not crazy about goat milk. You guys know Good Mythical Morning? What are their names? Rhett and Link. Yeah, Rhett and Link. Well, Rhett and Link, you guys know they do all kinds of crazy stuff on their show. One of the things they did is they tasted milk from many different mammals. And they said that actually, they had human milk, which they said seemed a little strange. They had goat milk. They had cow's milk. They had donkey milk. They said the donkey milk was actually really good. So I need to try donkey milk sometime. All right. So let's talk about fits, not the kind that your child throws, but let's talk about fits between parts. This is also related to tolerancing. A clearance fit is where there's always some space between the mating parts. So let's take it for instance. You guys saw me get out my camera and I had to extend the legs, right? So there's a leg that slides inside of one of the other legs. What kind of fit do you think that would be required there? A clearance fit, obviously, right? There has to be some space between those parts. The outside dimension of the leg that slides inside the other one has to be smaller than the inside dimension, otherwise it just won't fit, right? Or at least it'd be very difficult to get them apart. So usually we talk about fits in the context of round things, shafts and holes. And so in a clearance fit, the smallest hole is always bigger than the largest shaft. Because you remember, if we're talking about making a shaft, there's going to be tolerances on it. It's going to vary, right? It's going to, each part is going to be a little bit different. But as long as the male part is within tolerance and the female part is within tolerance, then the largest possible shaft in the tolerance zone will be smaller than the smallest hole for the female part. Does that make sense? So that's a clearance hole. I don't know if my page number references are right. I tried to update them when I went through and updated the 5th edition. I may have missed some.
Yeah,
Is that right? Okay, perfect, thanks. I want to go there anyway because there are some things to point out while we're there. Yeah, so on page 492, this table, table 13.3, is a table you'll see if you go into Machinery's Handbook. Machinery's Handbook has this table, but a lot more, because there are more sizes, more fits, more clearance specifications than just this. Class RC2, RC5, and RC8 are not the only ones. There is an RC3, RC4, and so on. But you may want to mark this page in the book with a tab, because it's one that you will have to reference. Now, there's another way of looking at clearance tolerances, and that's in a graphical form. You'll notice that this graph is on the facing page. However, let me warn you, while the graph is intuitive and fairly straightforward to understand, the table actually has more data in it. It has more information. So let's look at this figure in order to try and understand how the tolerances work for a clearance fit in this case. All right, so the upper part is the hole tolerance and the lower part deals with the shaft, okay? So the idea is that the basic size is just the nominal size. It's, and I think this is for a 2-inch. Yeah, if you look at the note, I cut it off on this, but on the bottom of figure 13.4, it makes a note that this RC fits the basic hole size of 2 inches. So the basic size, the nominal size of the hole and shaft is 2 inches. Okay, so that would be the diameter. But you'll notice that the tolerance zone on the shaft, if you have a very fine, an RC1 fit, is a very small tolerance zone, and it's fairly close to the basic size. But notice that the shaft always has to be undersized. And it looks like, let's see, 4 thousandths, 3, 2, 1. So the tolerance looks like it's a little less than 1,000, down to about a 1/2 thousandth or so. But notice the shaft always has to be undersized. In fact, we could look up this clearance if we have RC1. No, they got RC2. Let's move over to RC2. Notice it looks like that the tolerance on a 2-inch shaft is under by 1,000 to about a 1/2 thousandth. It looks like this may be 4/10 thousandths or so the way it's drawn. Let's look and see if that matches. So if you look in the table, table 13.3, you'll notice on the left-hand side are nominal size ranges. Well, a 2-inch size falls into what range? Exactly. You see the row that's labeled 1.97 to 3.15? That's the range that a 2-inch shaft would fall into. So what you can do is go over and look at the limits of clearance. Well, the limits of clearance mean that there's going to be at least 0.4 thousandths of clearance if you have an RC2 fit in a shaft that is a nominal 2-inch size. There could be all the way up to 1.6 thousandths of clearance. Does that make sense? And the actual tolerances on the shaft are, it has to be under by at least 0.4 thousandths of an inch. It could be undersized by all the way up to 0.9 thousandths of an inch. See how I'm reading these numbers off? Okay. How about the shaft? Well, how about the hole? Well, the hole could take on the basic size. In other words, the hole could be exactly 2 inches because the lower tolerance there is 0 thousandths over. However, the upper tolerance is 0.7 thousandths over. So what that tells us is that this point is at 0.7 thousandths. This is at 0. This point is at what? We're going back to the hole now, or to the shaft now. How much? 1.97? No, this is 0.4. Okay, so if you look at the shaft, and the numbers you see there are negative 0.4 to negative 0.9. See that? So this point is negative 0.4. This is not quite negative 1,000. This is negative 0.9 thousandths. Okay? You understand how this relates to what's in the book, what's in the table? Notice what happens. As you get to RC2, 3, 4, and so on, as the number goes up, the tolerance zone and the clearance increases. So these are sloppier fits on the right, and tighter fits or more precise fits on the left. Okay? Now, the numbers inside here, H5, H6, H7, and G5, F6, F7, those are standardized fits, and I can never remember exactly how they work. I know the capital H goes with the hole, but I can never remember what the number and the letter stand for. One is the width of the zone, the other is how far away it is from nominal, if I remember right. I always have to look. That's more common in metric, although you can technically use these for English sizes. But it's, even on drawings, it's very rare to even say I want an RC3 fit on this. Nominal size, 2 inches, give me an RC3 fit. The machinist will be able to look it up, but most of the time, with the tools we have today, there's no point in doing that. The best thing to do is simply put the tolerances on the part and look it up yourself and see what, that way you're controlling. You could argue that there's some design intent by including a note about RC4 on a drawing, but most of the time the tolerances on the hole and the shaft are just given in a drawing. Now, let me ask you a question. Notice something different about all the holes versus all the shafts? One fundamental difference here. Notice what it is?
Holes are always from 0.
The holes are always from 0. In other words, the holes can always be 0 deviation from the nominal size. They can always be at the nominal size. This is called the basic hole system. Okay, so this is a chart of tolerances for shafts and holes for different classes of fit in the basic hole system. It is possible to have a basic shaft system, where the shaft is the part that can always take on the nominal size. And in that case, if they were clearance fits, the hole tolerances would have to be skewed away from the 0 axis. That's not common. It's more common that this sort of the standard is the basic hole system. Okay? Like I said, there's actually more information in the table in a way than is in this chart. This chart is only good for one row in the table, right? It's only good for 2-inch shafts. Whereas the table actually has several different size ranges. Now, it's true that the graph has more classes of fit, but the actual tables in Machinery's Handbook have all of the classes of fit. Now, what you're probably asking is, okay, that's well and good. I see how I can specify the hole tolerance, but how do I decide? Well, there's some description on page 492 of an RC1 versus an RC9. Let's see if we can figure out which fit would be ideal for, say, the door hinge over there. Okay? We need a clearance fit, right, between the pin and the hole that holds that hinge together. What size would we want? Well, let's see. Let's go down to RC3, precision running fit. What does running mean? Running means that it rotates at a fairly high speed. Yeah?
So on your limits for your hole in your shaft,
Yeah.
I don't know, this might be a tough question.
No such thing. Go ahead.
There, so it says like for where we're at and for a 2-inch shaft, it would be for your shaft is -0.4 to -0.9. You said
Yeah.
that's tenths of 1,000?
Tenth of a thousandth. Yeah. Yeah. In other words, this chart, you're reading off thousandths of an inch.
Right. How do you know that it's thousandths of an inch?
Says it in the bottom.
Yeah, it probably says it, but I just know.
Oh, okay, I see it now.
Yeah.
All right.
Now, one thing that's confusing is the size range over here is in inches,
Yeah.
okay?
Yeah.
Which would make sense, really. It's the most convenient way for it to be. Good question. So your question was, how do I know that what's in the table is thousandths? It's from experience and from the note.
Well, I was just basing off where the decimal place was, but okay, yeah, I see that now.
Right, yeah. That's a good question that comes up frequently. All right, so let's see. So a precision running fit, an RC3, precision parts operating at slow speeds and light loads that must run freely. Changes in temperature may cause difficulties. Well, do we want that for the hinges on the door? Do we want the hinges on the door to lock up when it gets cold? No, right? So that's probably too tight a fit. Let's drop down to an RC5, a medium running fit. Accurate machine parts for higher speeds and or loads than for RC4. Well, this is not a machine part, right? It can be fairly sloppy and it really won't be a problem. It's just a door. Now, if this is we're talking about a heavy door, like a friend of mine loves Stargate. I don't know if you guys have ever seen this. I was introduced to Stargate. It has, what's his name? Richard Dean Anderson, is that his name? It was MacGyver. So she likes to call it Space MacGyver. But anyway, so it's a futuristic movie, and it's a super secret government location where they interact with aliens regularly and go to other planets regularly, and the general population doesn't know. And of course, they go on lockdown every now and then, because if you're going to have a show, you have to make it exciting, right? So that for whatever reason, they're going on lockdown again this week, right? And these are shows from the past; they've already been recorded. You can catch them wherever you want. But anyway, they've got, of course, when the base goes in lockdown, what scene are they going to show? They're going to show the huge, 20-ton door being closed automatically and locked into place, the solid, steel door. Would you want a fairly precise hinge on that or a fairly loose hinge? I think you'd want something more precise, because they're actually trying to seal the compound from the rest of the outside world. Okay? This is more like a blast door that's to protect against a nuclear bomb. Anyway, but for our doors getting in and out of the classroom, how about an RC7 free running fit? Reliable relative motion under wide temperature variations in applications where accuracy is not critical. Sounds pretty good to me. An RC7 might be what we want. Would you be wrong to specify an RC8? Permits large clearances, allowing the use of parts with commercial as received tolerances. No, that would be fine as well. Okay. The point is that you're the designer, and it's going to be experience that will differentiate a lot of these things. So there's some leeway in many things in this class, and that's just one. Questions, comments about fits? Okay, transition fits are fits where there may be clearance and there may be interference. It's possible that the shaft will be larger than the smallest hole. Okay? So this is a tighter fit where you need more precision. In fact, one place where transition fits are used is in cylinder heads. When you want to mate a cylinder head to a block, you don't just use bolts to do it. That's a bad idea. The bolts are not that precise. Instead, there are dowel pins that are used that are typically specified as a transition fit, and they have to be pressed in, and the action that presses them together is typically just bolting the head onto the block. Sometimes they're clearance fits. It just depends on the manufacturer. But anyway, transition fit may be clearance or interference, but interference fits are different, where the smallest shaft is always larger than the largest hole. So in other words, the shaft will have to be pressed into the hole for the parts to be assembled. If we turn the page a few over, page 495, you will see a table for what's called force or shrink fits, which these are all interference fits. These are all the same, different names for the same thing. Now, why are they called shrink fits? Well, they're called shrink fits because it's common to take the male part, which is larger than the hole, put it into a cold area to shrink it down, right? Use the coefficient of thermal expansion so that it shrinks. Take the hole part, heat it up, put it in an oven, for example, take it to 500 degrees, and then put the two together rapidly. And what happens is the hot part that has expanded will shrink, and the cold part will warm up, locking the two pieces together. When you do this, it can be actually very difficult to get the parts apart again. It can be very hard because the force between the two is so high. Well, I've been talking for about an hour. You guys are getting tired, I can tell. Why don't we take about a 5-minute break? I've got some parts in my office I want to bring down here that I've made. I'll tell on myself when I was a graduate student, and tell on my professor as well at the time, okay? We'll see you guys in 5 minutes.